So now that we have some idea about what a quaternion is, how to create a quaternion, and what a transformation matrix is, and how to create and manipulate transformation matrices, let's talk a bit about why they are actually useful. So inside Houdini, I'll just create a standard grid, disable the display normals, and use that as template point source for our copy to points. And I'll just copy our trusty old pig head, which I'll set to easy using the copy to points, which results in this. Viewport speed is totally fine, so let's crank this one up here. And let's not create a grid with 10 by 10, but let's say a grid with 100 by 100 elements. Takes a bit to create all those instances. And now let's move the viewport. And you can see that is quite stuttering. In this case, what I can do is head to my copy to points and check pack and instance. So on the one hand, you saw the update here was a whole lot quicker than when I increased the number of rows and columns here in the grid. And on the other hand, my point about the viewport is not existent anymore. Okay, so displaying your geometry takes about the same amount of time. However, there's this slight trick. It doesn't apply to any geometry. If you set your shading mode to smooth shaded, this is by far the fastest display mode there is in Houdini. Okay, back to my point. Let's modify this grid here again and set its rows and columns to 10 by 10 and again increase it to 100 by 100. And you can see now the copy to points updates much quicker. Let's increase this even further to 300 by 300. And you can see on the one hand, yeah, it takes a while, but it still updates in acceptable time. And also it does this here, where it has some LOD function and replaces the objects farther away with placeholder geometry, in our case, simple boxes. Oh, and I just accidentally dialed in 3000 columns here, so that's quite a lot. And you can see, not necessarily the viewport, but the updating process in here, in general, is much quicker than when we just uncheck this pack and instance. That is because when we middle mouse on this, we can see we have 90,000 points coming in through our grid here, and we got 90,000 primitives, and that is it. So what we're doing here is somehow not really creating geometry, but instead we are taking this geometry here, the pig head, pack it, that means we save its geometry at some location in RAM, and then just for each of those points coming through the grid into the copy to point sub, we just reference the points in RAM and just tell Houdini, please put the geometry that we saved at this other location onto this point. That in a nutshell is what packed instances does, or packed primitives. And let's dial the number back to something more human, like 10 by 10, so we can actually see something here. Let's highlight the copy to points, head into the geo spreadsheet. And you can see we've got all those points, all those template points, 0 to 99, so those 100 points coming through the grid. Let's head to the primitives. And yes, we see 100 primitives, but not much more. So how do we change their orientation? And yes, what I could do is I could create a normal attribute, for example, using a pointer angle after the grid here, and just write down some normal here. In our case, let's just point it in Z direction, like this. And we can see we can modify the orientation of those instances. Yes, we could also use a quaternion, So let's open up one of our last project files and copy this here. Remember, we created two quaternions using the lines here as an axis and then a float value as an angle. And we interpolated between those two to rotate this geometry here. Let's copy everything without the platonic. And in here, in our test scene, let's paste the whole thing. And instead of our geometry, let's wire up the template points in here and change some things. In the pointer angle, what we want to do, we don't want to rotate those points. We just want to save this rotation vector we calculated out to a point attribute called orient. And the shorthand for that is P for a vector 4 at orient equals to rot. That is our quaternion that we calculated. And now let's just wire this in the copy to points, highlight it, and in our pointer angle, let's dial in the bias so we can see we are interpolating between those two angles we specified, and writing it to an orient quaternion, and Houdini's copy to points automatically reads out an attribute called orient, which should be a quaternion, and uses it to actually orient the copies. So you could do that. Let's just undo it and wire in the grid directly. However, after you created those instances here, when you middle mouse on it, you don't see any attribute that specifies how they're oriented. So after you created them, maybe you want to modify their orientation. And yes, you can modify their position by just modifying their point position, so their P attribute. However, what if you want to rotate them? Well, again, let's head to the geo spreadsheet here and into the primitives. And there are no attributes. However, Houdini is just hiding something from us, which is called intrinsics. And let's just for a moment show all intrinsics that we have. So these are kind of hidden primitive attributes that Houdini creates and evaluates without your knowledge and without you doing anything. So it's got, for example, bounding box parameters here. It's got an ID for the geometry that's instanced there, an index, a few measurements. It's got an attribute that tells us how much memory is used for that kind of geometry, and so on and so on. Quite a lot, actually. And the main primitive intrinsic attribute we are interested in here, and let's hide those again, is called transform. And as you can see, when I check display transform, you see those are 9 values. And after the last 2 tutorials, you might speculate that 9 values, 3 by 3, might be a transformation matrix. And yes, you are right. Houdini, without our knowledge and without us doing anything, created a transformation matrix for each of those packed instances, for each of those primitives. So how can we read that out? How can we manipulate that? Well, let's add a point wrangle. And in the case with packed primitives and packed instances, both a point wrangle and a primitive wrangle should work because the point number, at least when those instances are created through a copy to points, is identical to the primitive number. So we can use either a primitive or a point wrangle. Doesn't matter in this case. So first, let's read out the current transformation matrix. Let's create a matrix 3 by 3. Let's call it TRN for transformation. And that equals 2. And let's use another function called primintrinsic. Again, let's go to the help page, and this one needs the geostream, the name of the primintrinsic to read, and the primitive number from which we want to read the intrinsic. So let's read from our current geostream the primitive intrinsic called transform, and from our current active primitive. Again, when the primitives come from the copy to points set to pack an instance, we can use the point number and the primitive number interchangeably because they're identical in this case. So add ptnum, and that should read out the primitive intrinsic. And in order to manipulate it, let's go back to our previous project file from the matrix tutorial. And in here, just copy the code that we used to generate the transformation matrix here and paste it in the point wrangle. And we're going to modify it a bit. On the one hand, we want to get rid of this because we already read in a matrix called TRN. And on the other hand, this is a matrix of 3. So this does not take into account translations. Let's delete that. And also this here. Let's also comment out the translate function here. And let's create the user interface elements here. So currently we are not applying the translation. We are just reading in our primitive intrinsic, created the sliders for the X, Y, and Z angle, and rotated our matrix by the X, Y, and Z angle along its respective axis. And then we also provided the same functionality for scaling. So after we did all that with the matrix TRN, let's write this back to the primitive intrinsic. That is done with a command set primintrinsic. Again, let's have a look at the help card, geostream, the name of the attribute that we want to set, the primitive number, the value, and then optionally the mode. So geohandle name, primitive number, same as point number in our case, and then the value. We just use that here. Well, that worked marvelously because we scale all our primitives to 0. Let's just scale them to 1, and here they are. And let's maybe head first into the edit parameter interface and give those guys here a decent range from -360 to 360. Let's do that for all of those angles here. And now dial in the rotation along those axes here. So now we can influence the orientation of those packed primitives, even after we created them using the copy to points. Finally, to take the translation into account, the way you manipulate the translation on packed primitives is just set the point position on which they are instanced. So in our case, we are running this in a point wrangle, and we are reading in the translate vector here. So after we did that, let's not translate the 4x4 matrix, which doesn't exist anymore, but instead, let's just set the current point position to its previous value plus the translate vector. Like this, and now translation should work. Yeah. Now we're translating those instances. So instead of uniformly translating them, let's, in our case, use maybe a noise to dial in the magnitude of the translation. So let's create a float, call it trans_amp for translation amplitude, and it should be equal to, let's use a simplex noise. As an input, it needs our current position, and let's increase the frequency by multiplying this position with a vector of 10, 10, and 10, like this. So now that we created the translation amplitude, let's just multiply the translation vector by it. And now you can see we've got this kind of random / noisy translation. We could do the same thing with the rotation. Let's just create this float before we do all the rotation. Let's create this up here and multiply the angles that we read in with the translation underscore amplitude. And in theory, I should create another variable containing a noise that's purely used to scale the rotations and then call this rotation underscore amp. But in this case, I'm just gonna be quick and cheap and use the same noise that I use for the translation. And now you can see not only is the translation, but also the rotation affected by this noise. Just so you can see, let's not scale the translation vector with the noise and just have the rotation affected by it. And yes, you can see those instances are oriented into different directions depending on where they are. You could of course do the same thing with the scale vector. I'll just spare you this. This is how you transform packed primitives even after you created them, which can be useful for a bunch of things. On the one hand, you can create motion graphics with them. Relying on instances saves you money, saves you calculation time, and once you know how to orient them, how to scale them, and how to translate them properly, they are really quick. And that basically is the secret sauce behind MOPs, behind motion operators, which Henry Foster and I developed. It just makes it easier for a non-coding Houdini user to manipulate instances and packed instances. On the other hand, this comes in handy when you are using packed primitives in a .NET to do rigid body simulation. So when you want to manipulate those instances while simultaneously running the simulation, that is a way to do it. So let's just quickly build something with what we learned. For example, the artwork that I used as a preview for these tutorials. And I did that, of course, using a copy to points. And on the one end, I fed in a box. I think I scaled it to 10 by 0.6 by 10, something like this. Then used a points from volume, which I was taught also generates points without a volume. I set the grid separation to 0.15 like this, and then wired this into the copy to points. And on the other hand, I created another box, checked at vertex normals, and set its size to 0.09, 0.02, and 0.09, so really tiny and a bit flat. While this in the copy to points, set this to use packed instances. So we got these bunch of plates here, and then I appended a pointer angle. In here, I first created a matrix, set this to be the identity matrix. Of course, I could have read in the primitive intrinsic, which in this case would be the identity matrix as well, so doesn't matter in this case. Then I created a float slider for the amplitude of that effect I'm going to create. Call it amp, create the slider, and of course this matrix should have a name. Let's call it TRN. And what I'll do then is create 3 successive rotations using an angle value. So float angle equals to our current instance's position in Z times our amplitude. And then I'm going to rotate our transformation matrix that we just created. I'll rotate it by this angle, and I will rotate it around the Z-axis. Let's check that is working. Let's just maybe increase the amplitude. Oh, and of course, we should write back this value. So set prim intrinsic, current geostream, transform is the name of the intrinsic attribute, point number equals to prim number in this case, and let's write back TRN. So now that is working. And you can see the rotation is dependent on where in Z space a primitive is located. So let's just copy this here and paste it 2 more times. Next, let's use the y-axis, so the position of our instance on the y-axis, and let's rotate it around the y-axis, and finally do this for the x-axis as well. Like this. We can now see those weird geometric patterns emerging. However, one thing that's irritating me is it looks as if those primitives here are intersecting. So let's middle mouse on this here. So that was just a display error that sometimes happens. Or I think maybe I still had this one ghosted here or something like this. Okay, so now you can see these structures emerging here, those undulating structures. And what you could do is, for example, type in an expression in here to animate this. So current frame number times 0.01, for example, as an amplitude, and then hit play. And you can see those undulating patterns animating, scaling through this field. And if you're a bit closer to the whole field, that gives a really nice motion. So that is how you build basic motion graphics using matrices, packed primitives, and primitive intrinsics.